Hello WebAssembly friends, thanks for tuning in to another episode. This one is all about the new command trigger for Spin. In this video we will get started with the command trigger, so we will build a hello world, we will spice that up a little bit to bring in some async capabilities, and then we will look at a real world scenario where you can make use of the command trigger when building apps that are executed on top of Kubernetes using SpinKube. That said, let's get started. This time we will start in the terminal. So I've already installed Spin in version 2.6.0 on my machine. And the command trigger is distributed as a plugin for Spin CLI. As you may already know, you can install new plugins from within the Spin CLI using the commands available at Spin Plugins. In order to get access to latest and greatest plugins, you have to do a Spin Plugins update first. So this one goes to a central location on GitHub and checks for latest and greatest plugins. Once your plugin feed has been updated, you can do a Spin Plugins list to get a list of available and installed plugins. And over here, down on the bottom, you can see trigger-command in version 0.1 is available. However, it's not yet installed on my machine. So let's go ahead and install that. And this is as easy as doing a spin plugins install trigger-command. Spin itself will ask again for confirmation to install the plugin, and you may already see that it identified my architecture. So I'm running macOS on an M3 MacBook, so that's an ARM architecture. Let's confirm the installation. And within a matter of seconds, the trigger command plugin will be installed and available on my machine. There we go. On top of the plugin, we also provide a template to get started as fast as possible with the command trigger. And to install the template, you can do a spin templates install, and you have to provide the repository where the template resists. And the repository of the command trigger is located at github.com/fermyon/spin-trigger-command. So we specify that one using the --git flag. As you can see, we now have access to the command-rust template. So let's use that and create our first Spin app that uses the command trigger. So that's spin new-t followed by the template we want to use, and that's command-rust in our case, and A to accept the defaults. Finally, we have to specify the name of our app, and let's call that one once. Let's move into the application directory and let's check what we got. So we got an application manifest, that's spin.toml, and besides that we get a Rust binary crate. This is not a regular Rust crate, it is a Rust crate that has been generated or bootstrapped using Cargo Component. And we use Cargo Component to compile our source code into a WebAssembly component. Let's open up VS Code and explore everything in more detail. So let's get rid of those notifications and let's start by investigating the application manifest. Over here you can see the trigger configuration. So we are using the command trigger, which basically runs our guest code to completion and terminates the host. So if we do a spin up right now, it will process or it will execute whatever is specified in our guest component, and then the spin host process will be terminated. By default, it is terminated with a 0 exit code. However, if we panic, then we can terminate the host process with a non-zero exit code, indicating that something went wrong. All right, let's jump right into the source code. And as you can see, this one is pretty bare bones, right? It just prints hello Fermyon to standard out. Those squiggly lines will go away once we build the app for the first time. Under the covers with BindGen is responsible for generating language-specific bindings, but as we haven't built yet, these are not available. So let's move to the terminal and let's address that. So let's clean it and let's do a spin build over here. So it downloads all the dependencies and we end up with a WebAssembly component. All right, let's clean the terminal again and let's do a simple spin up. And as you can see, our guest code gets executed, and if we echo for the last exit code, then we get back a 0. Let's move back to VS Code and let's change this implementation. But before we start with that, let's have a look at cargo.toml. And in contrast to a spin app that's created with a regular template that you may already be familiar with, like for example http-rust, there's an additional dependency which is spin-executor. And spin-executor allows us to use async capabilities such as outbound HTTP within our guest code. And that's exactly what we want to do for an example. So we can get rid of that print line statement over here and we can use the spin executor, which provides a run function. And this one takes an async move block over here. And within that block, we can use async capabilities. So we want to build a new HTTP request. And to do so, we can use the request builder from the Spin SDK and say, hey, we want to execute a GET request. And let me bring method into scope. That looks a little bit nicer. And the GET request should be sent to https://myip.fermyon.com. Let's copy that one. We need that URL in a second. And let's build the actual request. With the request in place, we can use the send function provided from the Spin SDK to send the request. Obviously, we have to await the response and we want to simply unwrap. So in the case of something going wrong, between my guest code and the remote server running in Fermyon Cloud, I want to simply panic at this point and terminate the host with a non-zero exit code. Finally, let's say we are interested in the response of this call. And I think we have to bring response into scope as well. Yes. And let's print something. So let's print line. Your IP is string : from UTF-8 lossy response.body. So you may already guess what this app over here, myip.fermyon, it's not fermyon.com, it's fermyon.app, by the way, what this app is all about. So that's an app I already deployed into Fermyon Cloud. I mean, actually it does not matter, but this one, just examines incoming requests and captures the callee's IP address from the corresponding HTTP header and sends it back as a response body. All right. One final step. Let's move back to the application manifest and let's add the URL to the allowed outbound hosts property on the scope of our component configuration. With that in place, let's save everything. Let's go back to the terminal and let's do again the spin workflow, which is a spin build and a spin up. And we should see our IP address or my IP address being printed to standard out. Next, we want to apply our new knowledge about the spin command trigger to unlock jobs and cron jobs in the realm of Kubernetes. I have already deployed a Kubernetes cluster and installed SpinKube, the open source stack for running WebAssembly workloads natively on Kubernetes on my machine. And I've prepared a sample application that's, mimicking a more realistic, like a real world scenario. The app consists of two Spin apps. We have one Spin app that exposes an HTTP API, and the API allows us to increment a counter, to ask for the current value of a counter, and to reset the value of a counter. The value of the counter itself is stored in key value store. And in Kubernetes, it's pretty common to use Redis or Wallkey, the fork of Redis, as a key value store. Besides the Spin app that acts as an HTTP API, we will have a second Spin app that is created using the command trigger. And we will package that one as a cron job. And for demonstration purposes, we will run on a tight schedule. So we'll invoke, or we'll ask Kubernetes to start that cron job every minute. And basically, this cron job goes to the same key value store as our Spin app that acts as the HTTP API and wipes everything inside of the key value store. So this is, demonstrating that you have an API that may be used by multiple clients, but on a regular basis, you have to do some number crunching, move data from A to B, or do some heavy computing. So common tasks that you would extract from your core application and run in a dedicated process where, no user interaction is required or expected. Let's move back to Visual Studio Code one last time to explore both Spin apps before we deploy them to our Kubernetes cluster. Over here in Visual Studio Code, you may already spot those two folders, API and cronjob, each containing a distinct Spin app. On top of that, we have two Spin manifests. There's spin.toml, which is the application manifest for HTTP API, and spin-cron.toml, which is the application manifest for cronjob. Let's start by exploring the API. Obviously, we have an HTTP trigger configured for our API that listens to all incoming requests and invokes the API component. We granted our component permission to use a named key value store called custom. Let's have a look at the API implementation. First, we use the HTTP router to lay out our API. And over here, you can spot those endpoints that I mentioned before. So we have get, post, and delete endpoints to interact with the value that will be persisted in key value store. Let's review the set value implementation. There is a call to get store, which is a method I wrote to prevent myself from, writing the same code again and again. But with the store in place, we use the getJSON function to load a value from key value store. If the value does not exist, we fall back to the default value of our Rust structure, which would result in us receiving a counter instance with a count set to 0. In either case, we increment the value in count by 1 and store the new value again in key value store. Last but not least, we construct an HTTP response that we send back to the callee. Let's also explore the cron job. The application manifest specifies a command trigger and points to the cron job component because that's the one that should be executed on that, tight schedule that we configure when deploying our cron job to Kubernetes. Looking at the source code, we can see that this also tries to load the name of the store from the application variables Then it tries to open up the store. With an active connection, we load all keys from within that particular key value store. And then we iterate over each and every key in that vector and delete the key from key value using the delete function provided from the Spin SDK. Finally, we end execution by returning an OK variant using a union tuple. Let's close the implementation of our cron job and let's explore the Kubernetes folder. Within that folder, you can find several templates. So let's start by looking at the template for the Spin app that acts as an HTTP API. It is basically an instance of the Spin app CRD, and this CRD has been deployed to your cluster as part of the SpinKube installation. In line 6, we define a token called artifact, and during the deployment script, we will replace that token with the actual reference to the OCI artifact of our Spin app. Also notice line 10, where we bring in the runtime configuration from a secret within the same Kubernetes namespace. Next, let's have a look at the cron deployment manifest. So this is a regular Kubernetes deployment manifest for a cron job. There's nothing special about it besides one thing, and that is line number 13, where we define the runtime class name. Again, a runtime class has been deployed to your cluster during the installation of SpinKube. If you stuck with the defaults, then the runtime class is called wasmtime-spin-v2. However, you can use kubectl get runtime class to check for the actual name of the runtime class on your Kubernetes cluster. Again, in this manifest, we use two tokens. So we have schedule, allowing us to inject a cron expression during deployment time, and we have artifact, which allows us to reference the OCI artifact of our Spin cron job. We also mount the runtime configuration from the corresponding Kubernetes secret. So again, you can see the RTC secret being referenced over here. Let's explore the template for the runtime configuration as well. So this one instructs Spin to use Redis if some component wants to interact with the key value store called custom. In our case, we have just one token over here, which allows us to replace or to put in the password that is generated during deployment of Redis to the cluster. Speaking about deployment, let's have a look at the deployment script. The deployment script starts with some, variable definition. Line 13, we can find the schedule variable, so that holds our cron expression. Line 16, we install Redis using the Helm chart from Bitnami. Line 19, we grab the password that has been generated during installation of Redis. And in line 22, we replace the password token with the actual password in the runtime configuration template. We store that to a temporary file called runtime-config.toml. Line 23 and 24 delete the secret RTC if it exists and creates it again in the default namespace using the previously generated runtime-config.toml file as the source for that secret. Starting line 28, we build and publish both Spin apps as OCI artifacts. Starting line 32, we start with replacing the tokens in the corresponding application manifests and deploy both apps using kubectl apply in line 35 and another kubectl apply in line number 39. Finally, we delete the generated files so that we have a clean Git state. Let's move over to terminal and let's deploy our app to Kubernetes. So let's go over here and let's move into the K8s folder. So this is where the deployment script resists. Let's do a deploy.sh, which will, install Redis in the first place. Then it will generate the secrets, which is already finished. Next, we will build and push the Spin app. So we start with building and pushing our API app. And once that's persisted in our registry, we build and push the cron job. Last but not least, both Spin apps has been created in the default namespace. So let's check. Let's do a kubectl get Spin app, and we expect API to be listed there. Let's also try a k get CronJobs. And as you can see, we have a cron job that's called Spin CronJob. It's active and last schedule was 3 seconds ago. All right, for every Spin app you deploy to your Kubernetes cluster, SpinKube also creates a service. So we can set up port forwarding to the service of our API, and we can use curl to invoke or to send requests to our endpoint. Let's use a post request to increment the counter. Let's go to localhost, I think it's 8080/value, and let's start incrementing this one. All right, let's check back with the cron jobs. So let's k get cron jobs again, and in 9 seconds we are due for another execution of our cron job. So right now we should find another job being created by Kubernetes. As you can see, 7 seconds ago, this job has been created. So obviously for every job, a pod gets spawned. So let's ask for k get po to get the pods. And the last one is already completed. So let's take a look at the logs which is a k logs. And as you can see, this one opened a connection to the key value store. It discovered that there is a spin counter value inside of the key value store, and it removed the key from the key value store. Which means if we again do a curl and not post, let's simply read the value of the counter, we expect to get back a 0. That's it. That's how you can build real-world applications with WebAssembly and Spin. The Spin command trigger ultimately allows us to build jobs and cron jobs, to extract long-running operations or tasks that must be executed on a regular basis into the counterparts that Kubernetes can manage and operate for us. What do you plan on building using the command trigger? Let us know down below in the comments. And by the way, don't forget to hit that like button and subscribe to our channel. See you next time.